Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello. I'm not getting feedback. That's probably because it's a good sound system, but you guys can hear me, right? Excellent. OK. Thank you. So thank you, everyone, and welcome back. I hope that you enjoyed your lunch. So this session is to talk about the Beneath the Surface program that has been run as a partnership between Microsoft Research, external research, and the Microsoft Surface product team. Now, I should mention that this was a joint effort here at Microsoft of a great number of people, and these are the folks who participated in that, and I hope that you'll have a chance to meet many of them here at the conference this week. But I wanted to take a moment to introduce the program and to talk about some of the projects that aren't going to be represented during this session, and then I'll introduce you to our two program participants and speakers. So I think most of you are familiar with Microsoft Surface. This device is one that has gotten a lot of media attention and generated a lot of excitement. Now, why we were able to put this program together with so much enthusiasm from so many people around Microsoft and from the academic community is because this device really represents an amalgam of a great deal of work, much of which was done in the external academic research community. And so we're so glad to have had the opportunity to have given back to that community with this program, and also to invite you to see the results of some of that work. Now, I should mention there are Microsoft Surface tables available for demo. They're out in the hallway over here. If you haven't had a chance to play with one yet, I encourage you to do so. And just to make it perfectly clear, these are now available for sale. And so all of the academics in the room who happen to know that I was on the Surface team, you don't have to email me personally anymore. You can just get one directly from the regular channel. I should also mention that as part of the NUI track that is happening at this year's summit, this session is part of that track, and also there'll be a demo of the Connect, formerly known by Project Natal, that'll be happening tomorrow in the Demo Fest. So let me talk a little bit about some of the participants in this program who weren't able to be here to present their work today. The first is Dr. Cha Shen, and Dr. Shen runs the program at Harvard's Initiative in Innovative Computing. I'll mention also Jake Wabrook, who is a professor at the University of Washington in the Information School. Professor Andy Van Dam, who I think actually is in the room. Oh, there he is. At Brown University. Professor Jeremy Bomberg, who I think is also in attendance this week. And Professor Ravan Balakrishnan of the University of Toronto. So all of these are exciting projects that have generated publications that we're excited to see coming out, and I hope that you will watch for those in the appropriate academic forums. But what I wanted to do now is to introduce the first of our two speakers who are going to present their research programs that have taken advantage of this research. So the first is Professor Mark Bolas from the University of South Carolina. Professor Bolas is a research scientist, artist, and designer who explores perception, agency, and intelligence. His work focuses on creating visual environments and transducers that fully engage one's perception and cognition and create a visceral memory of the experience. Amongst his courses at the undergraduate and graduate level are the design for interactive media and the business of interactive media. His thesis work, The Design and Virtual Environments, was among the very first to map the breadth of virtual reality as a new medium. He's been a professor at Stanford University and Keio University, and is chairman of Fake Space Labs in Mountain View, California, which he co-founded in 1989. So I'd like to invite Mark to come down and tell us about his research program that has included the Microsoft Surface table and some of the resources that have been made available by Microsoft. Professor Bolas.
Thank you, Daniel. Thank you, Daniel, very much. I don't know if this is on at the moment or not. Can you all hear me just fine back there? Great, thank you very much.
Sorry, I'm just...
No problem. He's operating a Surface right now. And he has to do it in the context of this room, which is very different than doing it in any way other than that.
There we go.
And that'll be part of my talk. Thank you. Howdy, thank you again. So this talk is entitled The Surface in Creative Production Environments. It started out as The Surface in Sound. And I'm an associate professor at the University of Southern California School of Cinematic Arts and also at the Institute of Creative Technologies. And at the School of Cinematic Arts, I've had the opportunity to meet a lot of people that are in the creative production side of things. Fortunately or unfortunately, the co-PI on this, not technically a co-PI, but my brother Nico Bolas is a record producer and engineer. And he's been really vital to this in terms of a lot of interviews I've done with him and then with two other people, George Massenburg and Richard Dodd, both very famous award winner, patent holder engineers. I was really lucky to have access to them. And then also a couple of musicians, high-placed musicians that are friends of Nico's, to see what they really want in the studio. And Blackbird Studio hosted some of this. But if you can't figure it out, there's nothing worse than having to work with your older brother. And he doesn't have any gray hair. And he would always say to me, I built this device once and it had a box, a switch box on the floor to change keys. And I made the box out of metal. The problem was that the musicians told me that if I made it out of wood, it would have sounded better. And my brother would tell you that that's true. And I'll tell him, no, it just makes you think it sounds better, Nico, but there's no difference between the wood one and the metal one. And I've always wanted to prove myself right. So there's a lot of papers now that prove me right. In the very recent issue of Science, but these papers have been around for a while, they've proven some things, such as if you give somebody a heavy clipboard and you ask them to, in this case, rate a candidate's resume on the clipboard, they'll rate the candidates with the heavy clipboard better. And, well, they'll rate the candidates as having a more serious interest in the position and also more likely to get along with coworkers because their resume was on the heavy clipboard. A really fun one is in the lower left. If you have the participants sit in a hard wooden chair or a soft chair when they're negotiating with a make-believe car salesman, when you ask them to make a second offer in a negotiation, they will interpret the other person as being harder in his offer, and they will be less likely to meet that negotiated offer on the second time around. And finally, if you ask them again with the heavy clipboards questions, they will almost weight, well, they do. They weight social issues heavier. Now, that one in particular is women do not and men do. But there's some really weird things about human beings. So maybe Nico has a point. If the musician thinks that the wooden box makes him sound better, then maybe the musician will act like it's making him sound better, and then he'll sound better. But he can't, Nico's not right. He also told me that digital sound sounded bad because it had harsh edges. So I started off with a goal that I found this magazine. I'm throwing away a whole bunch of stuff, and I found this magazine just in the last week, so I had to use it. 20 years ago, I said that the reason we use knobs is not because of the best way to interact with equipment, but it's the physical requirement of their function. And I thought that things like virtual reality would allow us to design new knobs that really allow us to have different kinds of fluency. So it's been exactly 20 years. And lo and behold, I have a Surface in front of me, and our challenge was basically to make a better knob. So the control you see in front of you there is a parametric equalizer, really simple one. You have the overall level of equalization. You have the center frequency. You have the Q of the curve. I'm wrong. I don't know what level is. You have the equalization level. You've got Q, and you've got frequency. And those are the basic things you can do in an equalizer. And if you notice, because the way that's laid out, you can get one hand in there, but probably not two. So we decided let's just do that. So here we're trying to design a better knob. And it's a simple EQ curve, but you can use both hands to control it. There's the center frequency. That's the Q. And you can use one hand to do these motions or two. And there's the overall amplitude. So with a very bad sound patch, you can hear what it does. So it's nice wide. And it'll start ringing as it gets narrow. Now we're notching something out. Now, one of the things this is letting the person do is control something in parallel. So you can't control both the high and the low end and move that together. And there's another thing about working in parallel, which is that you can do something in a single take of the song or a single pass rather than two. So if you're trying to mix, let's say, the drums and the bass, instead of having to, with a mouse, you have to listen to it and get the drum level just right, and then go back and listen to it again. That's very cumbersome and awful for music, because music is a very time-based thing. It only takes twice as much time, but the feeling doesn't come along twice. So that's how we decided to make a better knob. But when you really look at it and you start interviewing users, you find out that it's a very knob-centric viewpoint. This is the main studio at Blackbird Studio. It's gorgeous. And yes, there are a lot of knobs. And yes, it's hard to control them all. But if you look at the control room in general, it's more than just knobs. So you've got the patch bay, the digital audio workstation, outboard gear, and console. That's the logical environment. Those are all the signal flows and chains that you have to keep track of. You also have that studio door and a whole recording studio out there. But in addition to a logical environment, there's a collaborative environment. There's a second engineer, there's the main engineer, there's a producer, usually standing back there giving notes, and there's an artist. But in addition to the collaborative environment, you've got really a social environment. You've got maybe the wife and the ex-wife on the couch, and maybe the guy who nobody knows his name standing over in the corner. And I've been in lots of studios, and really that is what it's like. As people have been introduced to me before in the studio, "Hi Mark, I want you to meet my future ex-wife," and that's just taken for granted. It's a very strange environment. Behind that door, you've got a very strange acoustic environment. You have, just on the drum kit, 12 or more microphones just for drums. The room acoustics are very critical in where you place things, and in this room in particular, it's a gorgeous room. The entire ceiling can be lowered and raised to change the acoustics. You've got amps and mics over there by the guitar player, and this is just 2 musicians. There's multiple rooms and multiple areas. So the engineer's got to keep track of all of this, all the physicalness of it, all the sounds, all the patches coming in, the cables, and so forth. But as I'm saying, that's cognitively hard logically, which is my knob-based way of thinking, but it's also cognitively hard physically and emotionally. So yes, you have to set up the gear and twist knobs. Yes, you have to map the signal flow and figure out all the editing sequences. But you also have to be receptive to and match the feeling of the music itself. And that's kind of strange, but if the music's really going somewhere sad or happy, you had better be able to at least know that that's what's happening, because the artist is going to turn to you and say something about it, and you have to be keeping up with him. And then as a group, you're radiating body language. So you can't be like this. And you're also maintaining eye contact. If the artist turns to you to tell you something, you really don't want your eyes locked on the board and say, "Hey, just a second." Logically, you have to comprehend and communicate to other people these patches. And emotionally, you have to be sensitive to and possibly intervene in the session's mood. I asked my brother, what's the worst thing that can happen to a recording session to break its mood? And he said, "The girlfriend calls on one of these. The session is over." He will literally say, "That's it. Let's just come back tomorrow." So, sorry, it's a very sexist environment in the studio, so my examples are all very sexist, but that's what he said. So the next video is an engineer and the second engineer discussing how to record sound. It's a neat example because it's the recording sound to an analog tape, so it's actually a little more approachable from a video's perspective. And what's going to happen is they have to record. You only get 8 tracks on this one tape, so they have to figure out where the tracks are going to go and how they're going to record it. And it just sort of gives you a feeling of the studio environment. Daniel, when did I start?
8 minutes.
Thank you.
Okay? Yeah. Top to bottom. He's only going to play in the spectrum parts. Leave it muted except where he's playing. Then we're doing a live bounce of that plus castanets first tambourine part to track 3.
Look at the body language and the energy. This guy doesn't get it.
You need a bass player first before you start.
They don't have the bass player.
We erase 2 and 3. We do Spooner 2 and 3, bounce that to 8, finished.
How do we bounce and play back from one at the same time?
We don't. We record on 1.
I need Jeremy!
Then we bounce it to 3 with the
Live.
second overdub, live bounce. Then we re-record back over 1. So right now we have to do the double first, because it's simpler.
I ended on the group because that's the group of people that actually all have to work together to make that music. And throwing the surface in there is problematic at best. You can see how chaotic it is. But overall, what I really want to point out is worse than that is the fact that a lot of these boards are becoming just single screens with mice. And that's really problematic. And that is the tool that a lot of people are using these days. That studio is very unique in that it uses the old school knobs. So in looking at the problem, what we decided is that the main problem is that the engineer must be present. They have to be physically present, they have to be logically present, and they have to be emotionally present. What does present mean? I talked to many different people and we couldn't find a word to call it. Attention, cognitive load, there's lots of things to call it. Present was the one word that nobody had used yet, so I'm using it here. But basically what I'm trying to say is they have to remain aware and ready to act on all these different levels. So the rough equation we come up with is that a good interface is basically how effective it is at letting you get done what you want to get done, minus how needy the interface is. A needy interface is the enemy of presence. So we want to discover some user interface techniques that help you maintain whatever this thing called presence is. Now, for those of you that haven't tried it, and I'm not saying this because I got one, the Surface is just a fantastic test platform for this general study, not only for its own self. It allows you to experiment with classical visual interfaces, while at the same time it allows you to move tasks from the visual into the body. And it also is a great social platform just because of its form factor. And then, frankly, it's a really flexible development environment. And if it's additionally flexible, Disney Imagineering gave us some code that allowed us to port the basic gestures out and then port them into other applications. So not only can you use XNA for it, but we used Panda 3D, we could use processing, we could use Max MSP to do signal processing of the sound. It was a really flexible platform. And finally, it never crashes, and I know that sounds weird, and I knock on wood, but we've driven it in trucks to demos and never even had to recalibrate the thing. So creative production environments, 5 challenges. One is make better knobs. That's the one we just saw. We've got 4 more to get through here. The first is keep track of the mix. When you take the engineers out and you interview them, first thing they say is the physical stuff. I want better knobs. I hate the mouse. But after lunch or after a drink, what they really start telling you is one of their real problems, which is, I couldn't remember the name of the file, the take that we had. We did 7 takes, and the third one was the best one, and I forget what I called it. There's nothing that will get you fired faster than turning to the artist and saying, I don't have that take, which was the second problem they had, which is they go to do a final mix in another studio, and they find out that they forgot to bring that disc because there was one file, one little bit. Why is that? Well, let's say we're looking at mixing. You've got drums, then you add bass to the drums, you get a rhythm. Let's say you send the rhythm to the tape, or you send a recording of rhythm. That's why it's in red. Then to the rhythm, you add vocal and guitar. And then you decide to add some reverb to the vocal, so you go back and do that on another pass, and then you send that out to final. The problem is the artist might come back later and say, put some slap on the bass, which is a type of equalization curve. Well, the problem is that I sent it out to rhythm, which is already in a box. I already recorded that. And now I can't go back and change that part. And worse, he'll say something like, let's use the slap settings from the last song. So now I've got settings that I have to keep track of. I have recordings that were originally recorded from musicians, and I've got mixes that have been put down onto tape, so to speak. You have multiple versions of code and data, and these guys are just logistically in a bind. So how can we help them with their code and data? What happens when code and data are the same? Let's think about Lisp for a little while. So when you look at a single strip patch bay, if you really think about it, it's just a long Lisp statement. You've got all these nested equations of an overall gain control, but to that you're getting FX sends to other places in the studio. To that you're equalizing the sound coming in, and to that you're deciding how loud the sound coming in is. So in a way, that controller is equal to that Lisp statement. So Lisp would be pretty cool because then the actual sounds and the data and the control are all mixed together. The problem is, I mean, come on, we can't have them produce unmanageably long lines of Lisp code. So we thought about using the Surface to create a functional zoomable user interface. This doesn't zoom the image, it zooms the actual statements. So collapsing the statements is basically a 2-hand gather, and expanding the statements is a 2-hand spread. And what it means is that the statements can stay in place on the surface, so I don't lose where they are, and I can basically drill down as far as I want, or I can zoom back as far as I want. Now we go one step further, and we don't allow panning of the surface, and we don't allow clicking to zoom or even 2-handing to zoom. So it's really nice in that it optimizes the surface's work area. It's similar to mixing colors on a palette. We're going to show a video right now, but you're going to see a little segment in there. This was a quick representation we did. The little bars are sort of what a parentheses would be. In the long run, we want these representations to actually be the graphical representations of the elements you would see on a board. Here, the person is pulling apart. This is a fader control, but the fader control actually can be pulled apart to show that it has a max and a min value. He's going to drag a number in to change the min value, and then he pushes it back together again to be the fader. And you could collapse it one step more just to be a little, to be a nothing. So the idea is that you would dig in, do what you want to do, and then pull it all back together again to have a very simple control surface. So here he is, that's the fader. He decides he wants to change the min and max value on it. He spreads it apart, drops a number in, squeezes it back together again. And then there's the fader. Now this was a really quick prototype. We didn't actually do the animation of doing it with your fingers. We think there's a lot of power to that, but what we promised Microsoft we would do is think of lots of different gestures and user interface ideas. And so there's that basic idea, but we moved on because one thing is the ZUI feels great. The idea of a functional ZUI is kind of neat. And it could, we think, be mapped really quickly to existing digital audio workstations and, frankly, even possibly use a mouse or a two-finger spread to pull it apart, although the hands feel different. But it's really problematic to operate in real time, and signal routing and patching is not elegant. And then finally, it is a very needy design. It requires intense eye contact and precise picking of points. So for a single engineer working in a studio, which they do when they mix and nobody else is around, we think it could be a really good solution. For the engineer mixing with other artists, it's not going to work. And one of the reasons for that is in the next video where I interviewed Nico before we actually got the Surface and asked him what it was like to work with some artists. And he talked about one who's Neil Young and sings songs that have a lot of emotion in the song. And he talked about what it's like when you're working with him.
Not around you. You have to, and when it's coming through him, he has no control over it. He knows that there's a time limit on this burst. Yeah. We have to get it now. It's dumping, go now. Which is why, the worst thing you can do is not be in record.
Not be in record. You miss it. Not being record, in this case, in the old days, is analogous to not looking at him and knowing that it's time. So we moved on to something we called mix-up. The idea was, well, if we could simplify the surf Lisp controls into these boxes in the end that were just a fader, how could you use that in real time? And we had a structure that was really similar to Recording Console to do that. As a lark, one of the students broke that, and we really found that not having this structure was useful. And the user is allowed to draw the sound file as lines, but also to cross those lines with the finger orthogonally, and then that becomes a control. And one of the important things is that the way you draw it is not predefined, and what the control does is not predefined. You can change it later by taking a physical token, sliding it onto the surface, and sliding it off again. And then what that does is different.
Listen up, y'all.
So that's a fader. We're bringing in another sound here, adding another fader to it. There's a time bar at the bottom. And now we're going to add 2 more tracks. That's an overall volume level, so that just crossed all the lines. So now you can fade the whole thing down. Here's a case where you draw the control, and then in this case, the one on the right, we're going to do something with. So we mute them. Go to the one channel. And now bring a second sound path out. And draw something. We're going to do something to it, but that's not defined yet. Talk about it, and then you can't see, but just over the shoulder is the physical token, and that's changing what that control is doing. It's adding delay, you can hear it. And people did lots of crazy things with it. So just 2 quick paths. This is what one person did with it. And this is another one. Now, I don't know if that craziness does much good, really, but here's an emergent form that came out, which is this S. And the S allows a coarse level of control and a fine level of control in the same controller, which we never would have invented. And there's this other behavior that we found really interesting, which is, okay, now the guy's invented a control. Now he's going to take the control and slide it over to the other sound. You don't bring controls to sound. You patch the sound to the controls because they've always been physical. So the whole ordering of what does the control do and where is it becomes user-defined in time, and that's a very different way of thinking about it. So one of the conclusions from that is that the Surface is great because it allows the design of messy desks. You put everything where you want. Now, some of those patches were really messy. I'm not saying they'd be good in a production environment, but the fact that they allowed emergent control we think is really powerful. And because it's great for dabbling and doodling, where you put it comes from the user. So what it means to the user is already body-based, and there's studies talking about that. And more importantly, and one of our big findings in this is syntax. So my parents used to always say you could tell a Greek because of how they would form a sentence in English. My parents were Greek. And they would say, if somebody would say something like, throw the mop down to me, instead of they would say, throw the mop down to me, is how you would say it. Wait, throw me down the mop is how you would say it in Greek. In English, of course, it's throw the mop down to me. And the point is that really all you want to say is mop. And this syntax ordering, I think, is really interesting, not just on the Surface, but in terms of user design in general, where there's this syntax of you have to tell me what the file is going to be called, then you have to do this, then you have to do that, when the brain may not be at that point yet. And the thing we want to ask ourselves is, do you really need to know that right now? And what that the craziness showed us is that people like to order things very differently. They want to say, I want to do something to the sound, I don't know what yet. Then after they throw that thing on there, then they decide what to call the verb. It's almost a verb-noun sort of debate. So the point is, with the Surface, you don't have to decide all the time. You can let them decide. And then, of course, it leverages the user's spatial memory because they put things various places. The spatial memory, I think, is really good for what is a patch bay problem. So patch bays are really complicated, but actually the problem is they're pretty simple. I'm looking at all these cables around me now. And one of the reasons they're simple is because you can literally wiggle a cord and see where it goes in the patch bay, first of all. And second of all, you put all the cords there. So you know where they are. You've done some spatial mapping of it ahead of time.
Programming program. We're starting with a single node. I can move it with one finger. I can take a second finger and I can actually drag to create a second node attached. As you can see, the parent influences the child relationship. So I'm going to go ahead and create some more. Influences all of them. So here we go. As you can see, that only was one. Thanks. All of them.
Now, he's going to make a mess out of this.
So I'm going to actually erase it. So
he erases it, sorry.
So now I'm going to go ahead and connect these to that ones. Let's go ahead and connect that to that.
But you can still find the parent node and nodes underneath that really quickly by wiggling, which you'll see.
So what is related to what here? We can go ahead and wiggle and see that this influences
there's the parent node.
But these two.
So it's sort of the animation techniques we saw earlier today, but your body's involved. And we're starting user testing right now of actually putting things in front of people and seeing how quickly they can simplify them. The fifth challenge is keep my eyes on the board. So you could say you want a glance-only interface, but that's not completely true. What you want is to allow the person to look at it and memorize it when they have time to. And then when they've got to have eye contact somewhere else, they don't need eye contact there. It's another example of trying to get into the body as much of the interface as you can so the user doesn't have to use a lot of the body later. So to do this, but the problem is pop-up menus are good. There's a lot of, you don't just want to, you can't just throw all that stuff away. So one thing we tried was the idea of forcing the user to draw the menus by having them unfurl them. So so that's basically a menu. You unfurl it with your fingers, so now you've sort of memorized where it is. And then these have meaning. This is an analog fader. And the next one I think is a bidirectional switch. And now to close it up, you take your finger and close it up again. And then you can encircle it to unpop it. And we can have long debates about whether that's good or bad, and I'll talk about it a little bit.
Then I can also drop in
we put this together with the tree structure and physical tokens. And it allows a hierarchy to happen almost like the Lisp programming one did.
So we have three.
I'll just let it play.
We have all. So you can see there's 2 here, 3 there, and then all here. We can actually combine them usually. We can't combine them because they're not parent-child. When we make them parent-child, I can now just drop them in. And now when you see, I actually have more.
We think there's a lot of strength.
I can also pull out from it and make it a child node, like so. I can also go ahead and drop it back in.
Trees are your friend. Everything's a tree. Okay. Finally, we're trying to find ways to make it useful in things like Windows 7 and touch and multi-touch. In particular, here's a thing where you grab something and ask, okay, what uses this library? And then you wiggle it, and you see other things that use that library. And it's interesting because you feel like you're wiggling the other ones, because how do you know? The cursor's there, but they're all wiggling in exact time to your finger. This does not really work. That's just a quick flash prototype to see if we like the idea. But if anybody wants to do that, we'd love to work with you. Okay, so to recap, that's what we went through. And all we were after was some really early prototype gestures and interface concepts that hopefully can be used in things other than just the surface. So some rules. We decided that our basic design goal was, I put it there, you leave it there. And we want to make tools, not collaborators. We want to keep it dumb. So this meant that the user must touch everything, that the user interface may move nothing, including no zooms or pans, that no pop-up boxes or interruptions can happen. We don't want it to talk to you. No dialog boxes or words to read, because that steals eye contact. And no pre-ordered sequences of operations. In other words, let the user define their own syntax. Now, that's great, except what it really is, look, I'll do it, you won't. Don't touch it. Don't interrupt me. Don't even talk to me. Look, just let me do it my way. And then, hey, wait a minute, where are you going? I need a hand here. Right? If we really do that, we're asking the computer to basically go away. But the computer's got a lot of power. So what we did is we tried to stick with this as much as we could and then see how our hand was forced. So this idea of having to dig all the way in and dig all the way out and then put it somewhere, or we also have it where you can then throw it onto a tag and pull the tangible tag off the table to save space, is a way to solve some of these problems. How do you make magic with the surface? Some of the gestures work really well and some don't. And this is the way we're looking at it now. Agency is you say, I can do that. Efficacy is, I did that. And being a not needy interface is, and it looked easy. So we want a lot of efficacy with not a lot of neediness. And the agency sort of comes for free because computers are so damn powerful. Now, there's a second thing, though, we think about making something feel right, and that is that you have to do some work. Now, we're going to define work the way Newton did, just as force times distance. But notice that force has a vector. If you get the vector right in terms of orientation, and you make the person do a little bit of work, i.e. their finger has to move or push, but you can cheat the magnitude. I have the picture of the forklift because this is a forklift for my company, and I love it. It has this knob. I mean, I absolutely find complete joy in driving it. It has this knob on it made out of Bakelite. It's a Korean War forklift. And I can do that is I can lift 5 tons with this forklift. The efficacy is I pull the knob back and I lift 5 tons, and I just feel like God. And it's not easy. It's just a simple wheel and a knob. It doesn't. I can have eye contact. I can look what's going on. But it lets me get the vector right up, but it lets me cheat the magnitude. I pull back on this little tiny knob, and this thing just pulls up to 5 tons. It feels like magic. To me, the pinch to zoom gesture feels like that. I can zoom in. It's just amazing to be able to do that, but the vectors are right. So far, most of the things we've come up on the surface that feel right have the vector in the right direction. They're not pop that you can't point, you can't pop and click. There's no work there. But you can do that. You can erase, you can encircle, you can unfurl. You have to do a little bit of work. The surface is opening up new places. So situated cognition says that knowing is inseparable from doing. And what the surface really, and what this project has really been about, is a place. The place we chose was the recording studio, a collaborative production environment. The surface can fit into lots of places, so it's almost like a form of scientific instrumentation in that you can try it in lots of new places and see what works and what doesn't work. The desktop metaphor only had to work in the office place. Mobile devices and surfaces and whatnot are bringing us, it works in the bathroom, it works in the classroom, it works when I'm crying, it works when I'm mad. This doesn't work when I'm mad. I can't use it, right? But the situation is calling for different interfaces. And what the Surface really did for us was open up our mind to that. I want to point out that the Surface is like a drug. Microsoft gave us for one for free. We've since bought another one for an NIH project we just got, and we think we're going to buy another one as well. So be careful. And it's not a tablet. It's very manual. It's very physical. You get the body involved. A tablet does not do that. And I just wanted to show one more thing, which is cognitive load isn't just about memory. So I don't have the right term, but emotional authoring of something like music requires emotional attention, demand, and load. And a lot of our tasks these days have to do with this emotional demand that we have, as well as the logical demand. It's all technically cognitive, but when I use those terms, they mean a lot of different things to people. I'll end with this video, which is this term emotional author came up in my first interview with Nico before we had a Surface. We made one out of a piece of black foam core, and I sat it in front of him and asked him what he would do with it. And I'll just let that play. But he's talking basically about creative production environments, which I hadn't figured out yet, and about this emotional authoring stuff.
So we made this.
That's the imaginary surface.
So that this guy has this person here because he likes this person being there.
The engineer.
Then you get 3 horsepower because the energy gets exponential at that point. If this is a creative person who loves his tools and can make them happen without you knowing, and this person is a creative person who loves his tools and can come up with lyrics and music and you don't know how it happens, and the two of them collectively will make something better than singly. That's why there's good production teams. The closer we can get it to this, to the emotional author, the better it will be. And that allows the middle person to be more in tune with the emotional author side and not burden them with, I'm saving you because I understand this.
So it really bugged me because I found that video 2 days ago, and it's pretty much the conclusion of my talk, except I forgot he had said it. So don't tell my older brother that he was right, okay? I really want to thank Joe Logan and Joe Osborne, who had Annenberg Graduate Fellowships, Mark Monet and Bei Yang at Walt Disney Imagineering that provided us with the early code, a whole host of people who helped out, and John Nordlinger, who was backed up by Lee and Harold, as far as I can tell, who really pushed me to do the project. I don't think I would have pushed as hard. Microsoft Research really affords us an opportunity to research that few other places do these days. And then it's not a full academic talk, so I gave no citations, and it's hard to even know the right ones to use. Some places to start or look at is situational cognition, which was coined by the team with John Seeley Brown in '89. The ZUI, which both Ken Perlin and Jeff Raskin have done. Of course, Bill Buxton's work on multi-touch. And just in general, there's a lot of papers about spatial memory and touching and learning from that I think are quite useful to look at. Any questions?
Got a few minutes for questions? Well, I'll start us off then. So you showed the project that was inspired by a lot of the musical work, and you showed the sort of graph and the wiggling, the sort of very rhythmic idea.
Right.
And it's clear that there's sort of a musicality to that interaction. I wonder if you can talk a little bit about the connections between the first pieces that you showed and that sort of kinetic interaction.
The idea in that was to be able to find a way to mix the more the Lisp-like programming with the need for real-time interaction and flow. I don't think that answers your question.
Well, so is it the same? Does it come from the same place, from the design principles, or is there some connecting thread that?
Thank you.
Yeah.
If I go back to what I now have decided is that there should be a term called situational design or something similar to it, where what's the situation the person's in and what's the right user interface. So for the person noodling around trying to figure out the signal flow, the situation isn't a collaborative one where lots of people are asking him questions. So I think that Lisp thing could work very well. For the mixing one, that is one where there's literally a rhythm and time going to it, and there may or may not be other people. So the interface really has to take that into consideration and show a very different face. And so there's multiple tasks in the studio, and this isn't just really about studios, it's about the entire chain that's required to author emotional sort of content. And to do that, I think the situation changes. It's being sensitive to that situation that's important. And the Surface is one of the few interfaces that is flexible enough to fit different situations. I think that answered it.
So I wonder if you've gotten the mixing tool along far enough to test the idea of the final video. In other words, does it really help musicians bridge the gap between the engineer who has all the magic that the musician can't get to, and the musician gets closer to getting to the board in some way?
Right. Our goals for this project were to come up with some gestures and interface ideas that could lead in that direction. There's nothing I showed you that would stand more than 5 minutes in a real studio. That being said, some of those ideas, like the collapsing and pulling apart a Lisp-like syntax, I think that could fit right into a digital audio workstation project like Digitools. So in fact, we have some connections and we're starting to talk to them. I even think it could work with a mouse. Yeah.
I just wonder, you've lost the units in your buttons in this whole thing, you know, so do you have a memory, or how would, when you get it perfect, how do you, you know, if you have a 1 to the right and 2 to the left, this kind of thing, then you can write that down literally, but in your mixing, you lose your units in your interface. Is that a bad deal?
No, it's all, the where a knob is being recorded. And I mean, how they do it currently is literally on some of the faders, there's a motor, and you just move it. You're not paying attention to the actual numbers. You just move it to where it sounds right. And then the George Massenburg person was the guy who first did it. He literally just put a motor on the potentiometer and had it record where it was, and then you can play it back, and they're called flying faders. They go where you want. So now with mice, you don't physically have to move the knobs, but everything effectively, that control information is being recorded. And that's one, now they have a third piece of data they have to keep track of. They've got the mixes, they've got the original sounds, and they have all this control information, and they just get lost.
Thank you for the talk. As a recovering musician and producer, I enjoyed it very much. And one thing I'm wondering about is we've had digital audio workstations now for a while, and for some years it seemed like the paradigm that everyone was excited about was to then hook up physical controllers back up to the digital audio workstations. Mm-hmm. And I'm wondering why we haven't seen techniques like the ones you're now experimenting with come out of that paradigm. Kind of what there was, I was excited about it, and then something always left me wanting. I don't know whether it was that it was overly constrained by the physicality of the control, or that there was too much of a disconnect between what was going on in software and what was going on in hardware, or whether people were thinking too literally. Maybe you can.
I have a personal point of view.
Sure, I'd love to hear it.
Usually the physical controllers are this big. The board you saw there is a real mixing console. It's a 32-track board, and you saw that whole room, right? So the problem is that the problem is that they give you a little physical controller that's maybe a strip of 8, and then they map it to a screen, and then they have mode switching in the screen, and I think mode switching is the anathema of all of this. In that studio, mode switching is very physical. I literally will turn to the rack in the back. I'll turn to the digital audio workstation. I'll turn to the outboard gear. My mode switching is embodied. On those things, this little thing does everything, and I have to remember what its meaning is based on what mode the thing is on. And that is exactly what I'm trying to get away from. The brain can't, well, the brain can mode switch. There's cognitive loads associated with that, and it costs you time. If that time is half a second, and that's the half a second where you lose eye contact because you're trying to figure out where you are, that's a really long half a second.
Afraid that's all we have time for, but I'm sure Mark will be available to chat after the session.
I want you to know my proudest moment was figuring out how to make that thing pull the slide up like that. That was pretty cool. Thank
you. All right. I got this down now. I do. So next up, I'm very pleased to introduce Professor Steve Feiner of Columbia University. Professor Feiner directs the Computer Graphics and User Interfaces Lab. He is a co-author of Computer Graphics, Principles and Practice, an Introduction to Computer Graphics, and received an ONR Young Investigator Award. And together with his students has won Best Paper Awards at ACM West, ACM Chi, ACM VRST, and IEEE ISMAR. His lab created the first mobile augmented reality system using a see-through mobile display in 1996 and pioneered applications of augmented reality to fields such as tourism, journalism, maintenance, and construction. In recent years, Professor Feiner has been general chair or co-chair of ACM VRST, Intitain 2008. Do you actually pronounce it that way? Okay, great, Intitain 2008. And ACM WIST 2004, and the doctoral symposium chair for ACM WIST 2009 and 2010. Professor Feiner, thank you very much.
Okay. Thank you, Daniel. Take it the microphone is working. So this is kind of an omnibus talk, which I probably should go into regular presentation mode for. Good. Okay, so I'm talking about what I'll refer to as putting the surface in context, and it actually has two parts. In the first part, I'll be talking about some work that we've done on taking existing work on developing botanical field guides and trying to port it to the surface. And in fact, some of the stuff that we've been doing is now on exhibit at the Smithsonian National Museum of Natural History in DC as part of the Since Darwin, the Evolution of Evolution exhibit. And it's also outside if you'd like to go and try and play with it on the surface that has the leaf templates that you'll see sitting on top of it. And then the second part of the talk, I'm going to talk about some of the things we've been doing in experimenting with using surface along with other displays, sort of complementing the 2D horizontal desktop of Surface with tracked head-worn displays and tracked handheld displays. So to talk a little bit about the botanical field guide work, this work is built on a project that's joint between Columbia, University of Maryland, and the Smithsonian on developing electronic field guides. It was funded as an NSF ITR from 2003 through 2009. Peter Bellew-Murr is the PI, working with David Jacobs at University of Maryland, John Kress at the Smithsonian, and me and many, many, many students and co-workers. And that research has as its goal the development of field guides that, unlike the classical field guide that you hold in your hand, be it a book or, for that matter, an electronic one, were actually integrated with leaf recognition algorithms. So you could point a camera as part of the system or separate from the system, communicating wirelessly, and have the system be able to go and recognize a leaf and try to figure out what species it might be, and then work on really narrowing it down along with you, the expert botanist, using the system. So that system was indeed designed for, and in fact with, field botanists. John Kress, one of the co-PIs, is a botanist at the Smithsonian. And we had basically a kind of pipeline in which you start with the user photographing a specimen. The system then segments the image, matches the segmented image against species using algorithms developed by my colleagues, and then the user takes over and explores the ranked matches and tries to figure out from the ones presented by the system whether it might actually be one of those ranked ordered matches. So what we decided we'd try to do when the Surface rolled in the door was to see if we could adapt the flow of control, the workflow that we had used in a variety of previous systems, ones, as you saw, that were built on very large tablet PCs, handheld devices, and as well also smartphone devices, to see whether we might actually be able to do something maybe a little bit different on a surface. And unlike the model of a shutter release in which you essentially hold your camera or smartphone or tablet PC and take a picture consciously, we thought maybe we'd actually try the idea of just placing a leaf on the table and having it essentially capture that image. So I'm going to show you a little video of some of our very first explorations. And basically, this was very, very quickly done. Real credit to the work that was put into the Surface before we got our hands on it. Literally, in a little bit under a week, we managed to go and take a lot of stuff that we had done in other environments and port it onto the Surface. And so here you're putting a leaf on the Surface. It's actually using the IR camera to be able to go in and determine the shape of the leaf, and then do that using the matching algorithm to try to come up with a ranked set of matches. And then you can go and grab one of the images and do all the standard sort of like two-finger or two-handed stretching, scaling, rotating, translating that, of course, you'll see in many, many Surface demos. Some examples of so-called voucher specimens that are in the Smithsonian's collection that were digitized as part of that NSF-funded work. And we also commissioned a number of images from a really, really high-quality photographic team that you'll also see some examples of in the demo outside, which you can use to compare your specimen with. So one of the things that really became very obvious is that the model that we really wanted to have, which is just put the leaf on the table and have the system recognize it, is fraught with all sorts of interesting issues. Now what we see from above looking down is we put the leaf on the table, no matter what its shape is, and we see the leaf sitting there. Now what the computer sees, in this case, because it's an infrared camera-based system, is it's seeing essentially just IR being reflected from those things that reflect IR that are put on top. And in this case, what we're getting is reflections from 2 leaves. That looks pretty reasonable. Problem is that sometimes it's a big table, and there may be infrared sources of light above. Your arm, for example, as you get close, will actually do some reflection. The leaf, as you put it down, maybe even flutters down a little bit, and it may even see it before it actually touches. And so there's a bunch of other stuff that you might actually see. And if you're trying to recognize this stuff implicitly, it's a little bit different than holding really still, carefully framing your picture, and then pressing the shutter button. So in our sort of second try, we looked at how we might try to address some of these problems that occur when you've got all that surface looking out for IR being reflected. And some of the things we looked at were using a bounding box so that you only had to put the leaf in one particular part of the table, rejecting outliers that were deemed to be too small, for example, or not connected enough. Waiting for a stable image, so instead of simply taking the picture literally as soon as the table sees something, waiting a little bit to see if it might actually move a little, perhaps. Literally just giving up and retreating to using an explicit search trigger, and then finally also displaying the resulting segmentation just in case something went wrong. You at least want the person to be able to know why things aren't working by showing them literally what the segmentation is, as you can see, in fact, in that example at the top or underneath, hidden a little bit by the leaf at the bottom. We also played, in this case, because it is a big surface and it's nice and horizontal, and as we all know, that invites collaboration, we played with multi-user interaction in which multiple people might be either working together or, in this case over here, even working separately on the same surface. Now, while we were doing this, a very interesting prospect presented itself to us. As I mentioned, one of the co-PIs in the project is at the Smithsonian, and the idea of trying to develop an application that might be used in an exhibit had always been something that we talked about, and suddenly it became a very, very interesting prospect of trying to do something that would be part of a particular exhibit called Since Darwin, The Evolution of Evolution, that actually is ongoing right now at the National Museum of Natural History. And we figured, let's go for it. One of the things that made this particularly feasible is the Smithsonian, it turns out, had actually bought a bunch of surfaces, and they were sitting around and no one was really doing anything with them. So suddenly we went from thinking about things that were designed for use by botanists to things that were designed for the general public, things that were designed for people who were willing to spend some time learning how to use the tool, because scientists don't expect to be able to necessarily walk up and use something that they haven't used before. And now we have a general public who wants to be able to literally walk up and use, and has every right to expect that in a museum. And then finally, of course, no longer were we dealing with research, but rather more with something that, as part of this exhibit, was designed to be teaching. So this began to get very interesting very fast. We worked with a 10-person team at Columbia and the National Museum of Natural History, folks in research, folks in IT, folks in exhibits, folks in education. There was an iterative application development process that took many, many months with many, many different people to answer to. So there were folks who had different levels of say in, for example, graphic design and making sure things fit in with the exhibit, and making sure that things were worded correctly, as well as being scientifically correct, much more so than we normally would have to worry about working just by ourselves or working among folks at several different universities. We also were very intrigued by this idea of going from what were basically single-user applications to ones that might be designed to be single-user and certainly work for one person, but which could also encourage small groups of people who knew each other well to actually collaborate, cooperate together. And what we ended up doing, in fact, is the first Surface installation that actually has gone live at the Smithsonian. And when the exhibit ends over the coming week, it's actually going to move to another space there for at least another month. So what do we end up doing? Well, in the projects that I mentioned before, and the one, in fact, that you just saw in the video, we were taking real leaves and photographing them like a camera, or photographing them by having them sit on the surface. Instead, that just was not going to fly in a museum. You couldn't really ask people to bring leaves in. They would bring in things that were going to be crumbly or dirty or whatever. And so we sort of backpedaled to using leaf templates instead of real leaves for durability and lack of a mess. Instead of doing the segmentation and matching that we had done in all of our previous systems, for speed, because the algorithms took time, for robustness, we went to using so-called surface tags, little tags that are coded and recognized by the software in the surface. We went from this sort of scientific approach to creating a guessing game. And because we were trying to fit with the exhibit theme about the evolution of evolution, the tree of life, as first sketched by Darwin, ended up being something that was integrated into the application. And then finally, although we have not yet taken advantage of this, having only very recently finally gotten it into the exhibit, we instrumented it to be able to go and allow us to do user studies by essentially journaling up all sorts of different things that were happening during the course of use by museum attendees. So I'm going to give you a very, very quick kind of view. You can actually try it outside, as I mentioned. What we have on the right is going to be a little video shot from above of me actually using the system. And then because, you know, it's really a matter of our cameras not doing a very good job of capturing things, you can see how kind of dingy that looks. These are just plain old screen grabs on the left, which I've kind of synchronized with the video. And of course, the one thing you're not going to get from the screen grab is you're not going to see any of the things that happen with people's hands and the templates. And so you'll see that on the right, but you'll just see these sort of like changing, fading of selected screen grabs on the left over here when I play things. So we'll start with kind of the attract sequence, and then our person puts down a template, and we engaged in a little guessing game. In this case, they guessed correctly. Now they're going to select the part where they can find out more. And so they're going to scroll through a list of these nice images. They can scale them up and down, pick perhaps another one, be able to go and move it around, look at it. And having done that, they can remove the leaf. And if they put another leaf there, they can also get the same kind of quiz. In the interest of time, I've picked the right answer over here. A little bit more of the same. Here we're looking at some of the dried specimens that they have in the Smithsonian. These are actually the specimens you compare a sample with if you want to find out whether it's new to science or well known. And here we're putting another specimen on the right, and we can see how these two specimens are related in terms of the tree of life, which branches they each represent, and how they come to a common root over here. So, as I said, there's a demo outside. You're welcome to go and play with it. We've had very little experience with this so far. The student who did the majority of the work, Charlie Robbins, on this, hasn't yet had time, since he spent quite a lot of effort on this and is trying to also work on the outside. We haven't yet had time to actually start downloading any of the data that we've been journaling up to get an idea of how people are using it. And one thing we're hoping to do over the coming month, in a fraction that it's going to be there, is to actually do some studies where we vary some of the facilities that we present to people and try to see how they actually respond to those changes. One of the very interesting things about this kind of scenario is that people have gotten, at this point, very, very used to doing things with mice. There used to be the old joke about someone pointing with a mouse by taking the mouse up and kind of trying to touch the screen with it. You, of course, don't see people doing that anymore. And yet, with things that are tangible user interface based, multi-touch based, it's intriguing how people aren't really quite used to using systems like that yet, at least in the large. Of course, with the prevalence of Surface and its descendants, with a variety of multi-touch smartphone devices, we'll of course see people getting more and more comfortable with those kinds of interfaces. So I'm going to switch right now to talking a little bit about that other part of the presentation, which is the idea of using Surface with other kinds of displays. And one of the questions we're trying to address here, one that my group has actually been tackling for a while, is how you can take heterogeneous displays and devices, 2D, 3D, big, little, flat, vertical, handheld, head-worn, stationary, and essentially use them together to create interesting kinds of and hopefully effective environments. And so what in particular here we were looking at is how we could take Microsoft Surface and put it into a context of other devices, including, as I said, handheld ones and also head-worn ones. So we've tried a variety of different applications to get an idea of what sorts of things we might be able to do. The first one I'll show you is an attempt to make a very, very simple 3D modeling system, sort of a baby 3D modeling system. And what's interesting about it is it combines together the 2D surface with a 3D tracked head-worn display. And in this particular scenario that you're going to see, there's a camera in the head-worn display that's tracking a marker array, an optical marker array, that's actually projected on the surface. And this is built using the Goblin XNA infrastructure that my lab has worked on that runs on top of XNA Game Studio. So here we're seeing basically what the person wearing the head-worn display sees. What's a little bit interesting is that if you look at this carefully, you'll notice that there are objects like that cylinder, for example, on the left, that actually protrude up above the bezel, so to speak. These are often the kinds of images that you'll see in literature for 3D stereo display systems, just because it's so hard to see that it actually looks like it's in stereo. If you're looking at something that, of course, is a single eye view in glossy literature, people will often make images that you really couldn't make and never see in real life, in which things literally pop off the display, because they're kind of trying to get the point across, even though they're being a little bit dishonest in doing it. And here you can actually make things that literally rise up above and beyond the bezel that would normally cut them off when you're wearing and using this additional 3D display. So I'll show you a little video of what this looks like. This is shot through a head-worn display, one that is doing what's called video see-through augmented reality. So we're seeing the image shot by the head-worn camera, which is combined with graphics from another computer, and then essentially sent to the head-worn display, and in this case simply electrically split, so the VGA signal is also being separately recorded. We have a simple little model over here where we're sort of sketching out its footprint and then scaling it up and down. Using some of the basic surface menus, playing around with changing the color, for example. And then again, in addition to the idea that you're seeing all these things, of course, from the first-person perspective, depending upon where your head is positioned and oriented, again, you could do that if you actually were using, let's say, a rear-projected stereo display. But one thing you wouldn't get with a regular rear-projected stereo display is, again, this ability to have things that really extend beyond the space of the physical flat display itself. As, for example, you're seeing things over here that, again, are going above the edge of the table that you're looking at. And I think maybe at this point, probably I'm going to stop this over here. And so one thing we tried to do here is that, of course, if you're wearing a head-worn display, you will see a view which is essentially crafted for the particular position and orientation that your head is in. But what if you're not wearing a head-worn display? Well, the surface is there. You don't need a display being worn to be able to go and see it. And so one thing we were trying to play with was the idea that on the surface itself, we could be displaying things that were designed for people who weren't wearing head-worn displays. And in this case, we're displaying essentially the footprint of the object, maybe a little bit of additional information as you're seeing some of the readouts of the length of the edges in the bottom of that polyhedral object whose cross-section is in the process of being defined at the lower left over there. Here's another thing we were playing with. Since if you're wearing the head-worn display, you can't see inside of these objects unless you literally stuck your head into them. If you're not wearing the head-worn display, all you see literally is inside on the surface itself. And so we can put stuff inside of an object that isn't going to clutter and be seen by the person wearing the head-worn display, but which might be useful for the person who isn't. So in this case, we can actually have a little rendered view of what the person wearing a head-worn display would see from a canonical viewpoint. And there's some interesting issues over here of all of the stuff on the surface is being done in WPF in 2D. So how do we get 3D? We're actually running a separate display, running a 3D graphics package, and then shipping back as rendered textures to the WPF, which then gets displayed on the interior of the object as things change. So here's an example of a little real-time strategy game with the same basic notion that you could have things that a person not wearing a head-worn display would be able to see as kind of like 2D markers on a board, and yet a person wearing the head-worn display would be able to see things that really have this palpable sense of being 3D, view-dependent, and again not constrained by the bezel. So another domain that we've been playing with is urban visualization. And we're very lucky to get from Bill Chen and Johannes Kopf the textured building models from Virtual Earth for a major part of Manhattan, which you're seeing here, obviously rendered very, very small. And what we wanted to play with, again, is this notion of combining together the 3D seen on a head-worn display with the 2D on the surface. And in this case, we're using a slightly different way of tracking. Here, instead of having all the markers be on the surface itself, which needless to say kind of clutters up the surface, in this case we have a kind of a halo of markers that are on a printed board that's like a picture frame basically surrounding the part of the surface that actually is the display. And so here we can have models that, again, as you can see, extrude above the surface itself, and which have this very nice feeling of being like big plastic or wooden models without actually having anyone have to physically create them. In this case, as I said, we're tracking with a head-worn display looking at that frame of markers, and indeed there's also a handheld device over there that's being tracked by a completely separate system that has a set of these little cameras that are looking down and beaming infrared light that's reflected by these little retroreflected balls that are arranged in a rigid pattern attached to that smartphone. And that's being used to get additional information based on its position and orientation relative to where it's being placed in the environment. So here's another approach. In this case, using that same retroreflective marker tracking from the cameras above in the ceiling to track the head-worn display. And unlike the previous image that I showed you, in which you always have to be looking at the frame around the surface, in this case you simply have to have the little spheres that are attached to the head-worn display be visible by the cameras above, which, since they're above, means that they have a pretty good chance of not being blocked. And so here's an example of a Statue of Liberty model from Virtual Earth. Here are some buildings, including the Flatiron Building in Manhattan. And I have here just a little video of this running. And two things I actually want to mention about this is, one of them is that I've been talking about this being a surface. The videos you're going to see right now, and in fact the images I just showed you from this particular approach, are actually not running on a surface. They're running on a surface simulator running on a regular laptop, which is simply being held horizontally. These were made late last night by one of my students who's not in residence at Columbia this summer, and so he basically has set up in his apartment while he's working at Intel a set of these cameras overhead beamed down at the laptop being essentially held horizontally, which is being used along with a surface simulator to stand in for a surface. The one other thing is that he's actually recorded these using this system called Camtasia, which is really doing screen grabs and running on the same machine that's doing all the rendering, and that's usually a recipe for things running really, really slowly. So this is going to be kind of jerky. And boy, this is a lot jerkier than it should be. So if you give me 1 second, I think what I can do is to get out of here. And I actually have a lower resolution version of the video, which hopefully will play a little bit faster than that. Anyway, when this is not trying to actually record at the same time, it runs at a pretty reasonable clip, even on a fairly low-end machine. And then finally, in this case, we're trying to actually make sure that the stuff that was on the surface was going to be useful for both the person with the head-worn display and as well as someone without it. So you can see that we were not rendering things like the ground plane texture, so that was actually on the surface itself as opposed to being rendered on the head-worn display, and as well as also this little sort of banner of interesting places, potentially different layers, that would be used both by the person wearing a head-worn display and as well also by someone who is not wearing a head-worn display. Again, to try to let people with different kinds of capabilities interact with each other. So some of the things that we're looking at right now are, as I mentioned, this notion of collaboration in heterogeneous environments, people with different kinds of displays, different kinds of interaction capabilities, and what they can do together. And one of the things I think is especially interesting is combining together the sort of field guide functionality that I talked about in the first part of the talk with a 3D model of an ecosystem done using some of the stuff that I talked about in the second part of the talk. So you can actually look, for example, at species in situ and then maybe build up a model not just of I've seen this plant or I've seen that plant or this animal or that animal, but rather how they all interrelate spatially with each other. Using combinations of those different kinds of technologies. And finally, running out of time, I want to acknowledge the folks that funded and worked with us: John Nordlinger, Lee Dirks, Daniel Wigdor, Donald Brinkman, Microsoft Research in general for the generosity in this grant program and many other grant programs, the Surface team for their participation in this grant program, NSF for funding the work that led up to being able to actually build on top of it to make the surface-based field guide, our colleagues at the Smithsonian National Museum of Natural History, and my colleagues Peter Bellumer, David Jacobs, and John Kress, who are responsible for the really wonderful work that went into the earlier field guide research. And at that point, I think it's time to stop.
All right, we've got a few minutes for questions. Please raise your hand so a microphone can make it to you if you have a question.
It works. I want to know how many kinds of leaves can you recognize on the surface system?
Okay.
Yeah.
So there's nothing special about the surface system. And so the system that the Surface actually uses for doing the recognition, but not the one that we have here. The one we have here is just using those Surface tags. But the ones that we actually had done before, there are databases that we work with. The two main ones that we have are one for a little island that's beloved by botanists and naturalists in the DC area, which I think we have around 180 to 200 species, botanical species for that island. And then we also have another database for the sort of Baltimore, Washington area woody plants, like trees, for example, which is around the same number of plants with some overlap with the other one. In the first work that we showed you, we were using the infrared cameras in the surface to be able to reflect off of the leaf that would be put down on the surface. Now, the interesting thing is when you say really clearly, let's assume that everything is totally stationary and nothing's blowing in the wind, so to speak. Okay? The interesting thing is that when we take a picture in that sort of situation with a camera from above, okay, we often end up with situations where there are shadows, if you're not really careful about, hard shadows. And then the image that we take and that gets segmented often ends up being a superset of the actual silhouette of the leaf, because the recognition algorithms that are being used in this project developed by my colleagues are based on the leaf silhouette. Now, on the surface, you get kind of the opposite approach, because it's imaging up from below. If you have something that's curling up a little bit, instead of it casting shadows, the parts that curl up are not actually reasonably in focus, and consequently you end up with kind of an erosion of the silhouette, and you get kind of a subset of it. So in a situation in which you have that leaf really, really flat, normally when we take pictures we try to sort of hold it down with double-sided tape to make things really fair and keep out of direct sunlight, casting shadows. But if we do the same kind of thing on the surface, we get essentially an image of comparable quality in terms of what the algorithms need, and it will handle just as well as well-taken photographs using the same databases that we do for the earlier versions.
So, Steve, there's a whole variety of technologies for surfaces, and one of the interesting things about Microsoft Surface is that, like other surfaces, it uses cameras of a certain style. It's been appropriated in some ways to also do fiduciary markers.
Mm-hmm.
In your case, if you had to actually say, let's actually redesign another surface that lets me do the stuff I want,
mm-hmm.
instead of it just being by accident because they wanted to, that's how they implemented touch, what would you want to see in a surface to let you do the kind of stuff that you want to do?
Okay, so that's a great question.
Yeah, essentially I wanted more than by accident or circumstance.
So for right now, for example, the surface, the picture it's taking, we're lucky that those particular algorithms that we're reusing really used only the silhouette. Okay, if they used color, for example, we'd be dead in the water because the surface doesn't see color, it only sees infrared being returned by things that are reflecting it back. And so I would want to have something that was sensitive to color, for example. I would want to have something that ideally would have, say, a depth camera in it of some sort. I think I would like to have something that was not just sensitive to different kinds of light, but which is also sensitive to, for example, real genuine touch. So it might actually be monitoring the pressure that I'm putting on something, and not just by seeing sort of like, more I push, maybe the more my finger gets flattened against the surface and the better it's being imaged. I'd like to have something that really can tell about the pushing down on it. I think I would want to have higher resolution, both in terms of the display and also in terms of the perception on the part of the surface. And I probably would also want to have a higher frame rate, both in the display and also in whatever sensors there were that were listening and looking at stuff. So if I move my fingers very, very quickly, I'm sure Mark probably has the same issue. One wants to be able to go, and when you make music or mix music, you want to not have to be constrained by the frame rate of the cameras. And I don't want to be constrained in interactions that I do from not having to move at speeds that I like to be able to go and move at.
I think that's all the time we have. Thank you very much. Thank both our speakers, please.